We just finished talking about the mole as a concept and about molecular weight, and I want to connect this now to molecules as well. So let's look at the formula unit for an ionic compound just as an example. We could use any. And let's look at this sodium chloride. We know that one unit here is made up of one sodium, and it happens to be a sodium ion, and one chloride ion, right? And we figure that these guys go together and then they stick because they're attracting each other, and then they form this one unit. So if I have one molecule, they aren't really formally molecules, but anyway, you still use that word, or you can say one unit of NaCl that contains one sodium ion and one chloride ion. Right, Na plus and one Cl minus. So now let's think about a mole. A mole is just a collection of a bunch of stuff, right? 6.022 times 10 to the 23rd things. So if instead of thinking about one molecule, one unit of NaCl, what about we think about one mole of NaCl? And the abbreviation for mole is MOL. It's not much of an abbreviation, but people still write it that way, and so you need to know. 1 mole of sodium chloride. So for each unit of sodium chloride, it has 1 Na plus and 1 Cl minus. So that means that 1 mole of NaCl also has 1 mole of Na plus and 1 mole of Cl minus. Now, occasionally I have students who have a hard time with this. They say, well, we take 1 mole of this and 1 mole of this. How do we not have 2 moles of things? We do, except that they combine to make 1 unit. So think about a car. It doesn't surprise you that a beautiful car like the one I just drew has 4 wheels. It has headlights, it has taillights, it has windows, it has windshields, it has doors, all these things, right? And even so, it's still one car. And so it's the same way when we take particles, individual particles, and then we turn them into a molecule. Just like the car, they just make up parts of the car. So the sodium and the chloride together make one NaCl, just like all the parts that make up a car make one car. Okay? So we have 1 mole of each of our components when they are 1-to-1 in a sodium chloride because we have 1 mole of sodium chloride. The same thing is true when we write a balanced chemical equation. So one of the first equations I wrote was this carbon atom reacting with an oxygen molecule to make 1 molecule of carbon dioxide. And this is also true if we have 1 mole of carbon reacting with 1 mole of O2 to make 1 mole of CO2. And in fact, when we write this equation, we aren't usually thinking about the individual carbon particle and the oxygen particle and the CO2. We're thinking about a collection of particles. And these are all a 1-to-1-to-1 ratio in this particular equation. And of course, we've seen that lots of different equations exist with lots of different ratios of elements. And so the mole relationship is exactly the same as the atom or particle relationship here. And this big idea is called stoichiometry. Stoichiometry is the way of thinking about the ratios of how things react. Sort of the proportionality of different materials for each other when they react together. However, it's great to think about these moles, but in lab, of course, we use grams. That is, grams, milliliters. These are the things that we use to measure. So if we have 1 mole of carbon that is going to weigh 12.011 grams, what about 1 mole of sodium chloride? We know that this is made of sodium and chloride, and I hope you remember that the masses of these electrons, the electron that's missing from here and got transferred to here, these masses of these electrons are insignificant. And so the mass of a sodium ion is basically exactly the same as the mass of a sodium, and the mass of a chloride ion is the same as the mass of a chlorine atom. So that means that if 1 mole of sodium chloride contains a mole of sodium and a mole of chlorine, then we can take the masses of the sodium and the chlorine and we can add them together and get the mass of the sodium chloride. So if we refer to the periodic table, you can pause the video and go take a look and collect the masses of the sodium and the chlorine. On my periodic table, I have 22.990 grams per mole. I'm using the one in the book. And 35.453 grams per mole for chlorine. So if I add these two up, then I should get 58.443 grams per mole. So 1 mole of sodium chloride weighs 58.443 grams. Okay, this is all very well, but let's go ahead and take a quick break here. I took a video because I happen to have sodium chloride at home. Most of us do. It's table salt. So I wanted to see how much 1 mole of sodium chloride actually was. Like, how much space does that take up? I don't have a very good sense for grams, so I'm going to switch over to a little video that shows me weighing this out, and we'll take a quick look at it. Okay, here's my little balance, and we can see the numbers, so I tare it. And now I want to weigh some salt. I'm using some kosher salt because it doesn't have any additives in it. So I'm going to use some good technique, take my container off of the balance to pour into it so I don't spill on my balance. Let's see, that wasn't enough. So I'm going to put a little more in. Remember, I'm going for 58.443 grams. Nope. Still not enough, still working on it. Okay, a little too much this time. So we'll take a little bit off and we should be pretty close. All right, we have 58. So we're pretty close to, 58.53 grams. So just over 1 mole of salt. So how much is that anyway? I emptied out my cup measure. There's a 1/3 cup measure. So let's take a look. It looks pretty close. I probably should have moved my balance so I wouldn't spill on it. All right, so it doesn't quite fill up a 1/3 cup, so let's go ahead and try a 1/4 cup. In fact, that is basically just the right amount, 1/4 cup of salt. All right, so we found that 1 mole of salt takes up pretty close to about a 1/4 cup. And so that's a pretty concrete thing for us to be able to get our heads around. So we can measure masses of reagents, and then we can figure out how many moles they are. So let's go ahead and try this again. Let's find let's play around with some silver nitrate as well. So let's ask the question, how many grams are in 0.150 moles of silver nitrate? Another way of saying this would be, how much does 0.150 mole of silver nitrate weigh? So, what are we going to need for this? If we want to know how many grams and we have moles, we always will have to calculate the molecular weight. And that's the thing that we just did up here for the sodium chloride. So, I'm going to say that again. If we're talking about gram to mole conversion, we always need to calculate the molecular weight. So let's go ahead and do that. We're going to use our periodic table a lot, so it's a good idea to have one handy when we're doing these kinds of calculations. So from the periodic table, I can find that silver has an atomic weight of 107.87 grams per mole. Nitrogen has 14.007 grams per mole. And oxygen has 15.999 grams per mole. Now, when we look at this this chemical formula here, we can see that we have three oxygens based on that subscript. So that means that I need to multiply this mass of the single oxygen by 3 so that we can have all three of those represented. So we're going to now sum those all up. So pull out your calculator and do this, and you should find that the total mass, if I did it right, is 169.87 grams per mole. And I'm using significant digits here. I have addition rules, and I have 2 decimal places and 3 decimal places. So I'm going to keep 2 decimal places in my answer because this is addition rules. Okay, so did we finish calculating what we needed to calculate? No, right? The question was, how many grams are in a fractional number of moles, not a whole mole? If we wanted to know how much was a total mole, yes, 1 mole of AgNO3 does weigh 169.87 grams. That's true. But we don't have a whole mole, we have 0.15 moles. So we're going to take 169.87 grams in 1 mole, and we'll multiply it times the 0.150 moles so that those mole units will cancel out and they will give us grams. So when we solve for this, you should get, if I did it right, 32 point, oops, sorry, I was looking at the wrong number here. We should get 25.5 grams. So we can do this the other way too. In this step, we started with moles and calculated grams. But we can do the other direction too. We can ask a question like, how many moles of silver nitrate are in 41.69 grams of silver nitrate? In this case, we're going to do exactly the same thing, only we're going to pay attention to where the units are so that the gram unit cancels out and the mole unit is what's left over. So the molecular weight acts like a unit conversion. I mean, it is a unit conversion. So we will have 41.69 grams. We always start with the number that we were given. So here it was 0.150 moles. Here it's 41.69 grams. And then we use the molecular weight. I guess I did the molecular weight over here first, but same idea. But here the grams go on the bottom and the moles go on the top because I want to divide out the grams. So 1 mole of silver nitrate weighs 169.87 grams. So the number of grams go on the bottom because we're dividing out the grams. And when you do this math, you should get 0.2454 moles of silver nitrate. Okay. Now the reason why we really like using these gram to mole conversions is that, for example, let's say you read a journal article about some research that you want to do. And the journal article says that you need to use 0.1885 moles of silver nitrate for a reaction. Now, we don't have a measuring system that will allow me to just directly go into the lab and measure moles of something. Instead, we always have to use grams. So we're almost always going to be converting between grams and moles. So in this case, let's practice it again. Calculate the grams. Pause the video and go ahead and do that. You should have found 32.02 grams of silver nitrate are what you need to weigh out if you want 0.1885 moles of silver nitrate for your reaction. So let's do a little extra practice. Let's calculate the mass of 1.914 moles lithium carbonate and calculate the number of moles in 62.51 grams aluminum oxide, Al2O3. All right, pause the video and go and try those out. Okay, so for all of these reactions, our step 1 is going to always be to calculate the molecular weight. So you should have found that there are 2 lithiums, 1 carbon, and 3 oxygens, and that gives us a molecular weight of 73.89 grams per mole. And then multiplying the molecular weight times the moles should have given us 141.4 grams of lithium carbonate. Please do tell me if I happen to make mistakes in here. It happens. Okay, so for the second problem, you should have found that the molecular weight was equal to 101.961 grams per mole because there are 2 aluminums and 3 oxygens here, and that this will get us 0.6131 moles of Al2O3. Now, I want to stop for a second here, and I want to talk about a slightly separate concept that is really connected to what we're doing here. We said in 1 mole of carbon dioxide, there are 1 carbon and 1 O2 that make up these guys, right? 1 mole of each of those. So let's just talk about the elements now, all right? So in CO2 in 1 unit, we have a carbon, and it's bonded to 2 oxygens, right? So if I just want to look at the elemental ratios here, in 1 mole of CO2, I have 1 mole of C and 2 moles of O, right? Because this O2, it has 2 oxygens. And so the mass of that O2 is twice the mass of a single oxygen. And so that was why we added those together. All right, so let's make this a little bit more challenging now. If we have 0.6131 moles of Al2O3, now how many moles of O, just O, are there? This is a molar relationship that we can see by looking at the formula unit that we have right here. We can see that for 1 Al2O3, there are 2 aluminums and 3 oxygens, whether we're talking about atoms or whether we're talking about moles. So that means that we can write this relationship as 1 Al2O3 goes to 2 aluminums. It relates to 2 aluminums, which relates to 3 oxygens. Okay, so we can write this as a systematic relationship, as a ratio. In 0.6131 moles of Al2O3, we can now say that 1 mole of Al2O3, I'm putting it on the bottom because I want to cancel out those moles, has 3 moles of oxygen in it. So the total moles of just oxygen in 0.6131 is 3 times 0.6131, or 1.839 moles, keeping only 4 significant digits, because that's how many we start with. We're going to do a lot of these kinds of relationships of looking at mole to mole ratios, and so I want you to start getting comfortable with them.